Sections 5 through 8 of On the Elementary Electrical Charge and the Avogadro Constant. Physical Review, Volume 2, Number 2. By Robert Andrews Millikan. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Section 5. The correction term constant, capital A. This constant was before graphically determined, 1c, page 379, by plotting the values of e sub 1 to the 2/3 power as ordinates and those of L over A as abscissae, and observing that if we let x equal L over A, y equal e sub 1 to the 2/3 power, and y0 equal e to the 2/3 power, equation 3 may be written in the form equation 8, y sub 0 times open parenthesis 1 plus capital A x close parenthesis equals y, or equation 9, capital A equals dy dx over y sub 0 equals slope over y-intercept. Now, even if the slope were correctly determined by the former observations, all of the above-mentioned sources of error would enter into the value of the intercept, and hence would modify the value of capital A. As a matter of fact, however, the accuracy with which the slope itself was determined could be much improved. For with the preceding arrangement, it was necessary to make all the observations at atmospheric pressure, and the only way of varying L over A was by varying A, i.e., by using drops of different radii. But when A was very small, the drops moved exceedingly slowly under gravity, and the minutest of residual convection currents produced relatively large errors in the observed speeds, i.e., in E sub 1. If, for example, the time of fall over a distance of 2 millimeters is 20 minutes, it obviously requires an extraordinary degree of stagnancy to prevent a drift in that time of, say, 0.2 millimeters due to convection. But this would introduce an error of 10% into E sub 1. Furthermore, with these slow drops, Brownian movements introduce errors which can only be eliminated by taking a very large number of readings, and this is not in general feasible with such drops. It is quite impossible then, by working at a single pressure, to obtain from the graph mentioned above a line long enough, 1c, page 379, to make the determination of its slope a matter of great precision. Accordingly, in the new observations, the variation of L over A was effected chiefly through the variation of L, i.e. of the pressure P, rather than of A. This made possible not only the accurate evaluation of E, but also the solution of the interesting equation as to the law of fall of a given drop through air at reduced pressures. Section 6. Method of testing the assumptions involved in the oil drop method. In order to make clear the method of treatment of the following observations, a brief consideration of the assumptions underlying the oil drop method must here be made. These assumptions may be stated thus. 1. The drag which the medium exerts upon a given drop is unaffected by its charge. 2. Under the conditions of observation, the oil drops move through the medium essentially as solid spheres. This assumption may be split into two parts and stated thus. Neither, to A, distortions due to the electric field, nor, to B, internal convection within the drop, modify appreciably the law of motion of an oil drop. 3. The density of oil droplets is independent of their radius, down to A equals 0.00005 centimeters. Of these assumptions, 2a is the one which needs the most careful experimental test. It will be seen that it is contained in the fundamental equation of the method, C7, which may be written in the form equation 10, E sub n equals fraction, numerator mg, denominator capital F v sub 1, and fraction, times open parenthesis, v sub 1 plus v sub 2, close parenthesis. Or still more conveniently, in the form equation 11, E sub n equals fraction mg t sub g over capital F, end fraction, open parenthesis, 1 over t sub g plus 1 over t sub capital F, close parenthesis, in which t sub g and t sub capital F are the respective time intervals required by the drop to fall under gravity and to rise under the field capital F, the distance between the crosshairs. In order to see how the assumption under consideration can be tested, let us write the corresponding equation after the same drop has caught n prime additional units, namely, equation 12, E sub n plus n prime equals fraction mg t sub g over capital F, end fraction, times open parenthesis, 1 over t sub g plus 1 over t sub capital F prime, close parenthesis. The subtraction of 11 from 12 gives equation 13, E sub n prime equals fraction mg t sub g over capital F, end fraction, times open parenthesis, 1 over t sub capital F prime minus 1 over t sub capital F, end parenthesis. Now equations 11 and 12 show, since mg t sub g over capital F remains constant, that as the drop changes charge, the successive values of its charge are proportional to the successive values assumed by the quantity 1 over t sub g plus 1 over t sub capital F. And the elementary charge itself is obviously the same constant factor, mg t sub g over capital F, multiplied by the greatest common divisor of all these successive values. It is to be observed, too, that since 1 over t sub g is in these experiments generally large compared to 1 over t sub f, the value of this greatest common divisor, which will be noted by open parenthesis 1 over t sub g plus 1 over t sub f, end parenthesis, sub 0, is determined primarily by the time of fall under gravity, and is but little affected by the time in the field. On the other hand, equation 13 shows that the greatest common divisor of the various values of 1 over t sub f prime minus 1 over t sub f, which will be designated by open parenthesis 1 over t sub f prime minus 1 over t sub f, close parenthesis, sub 0, when multiplied by the same constant factor mg t sub g over capital F, is also the elementary electrical charge. In other words, open parenthesis 1 over t sub g plus 1 over t sub f, close parenthesis, sub 0, and open parenthesis 1 over t sub f prime minus 1 over t sub capital F, close parenthesis, sub 0, are one and the same quantity. But while the first represents essentially a speed measurement when the field is off, the second represents a speed measurement in a powerful electric field. If then the assumption under consideration is correct, we have two independent ways of obtaining the quantity which, when multiplied by the constant factor mg t sub g over capital F, is the elementary electrical charge. But if on the other hand the distortion of the drop by the field modifies the law of motion of the oil drop through the medium, then open parenthesis 1 over T sub G plus 1 over T sub capital F close parenthesis sub 0 and open parenthesis 1 over T sub capital F prime minus 1 over T sub capital F close parenthesis sub 0 will not be the same. Now a very careful experimental study of the relations of open parenthesis 1 over T sub G plus 1 over T sub capital F close parenthesis sub 0 and open parenthesis 1 over T sub capital F prime minus 1 over T sub capital F close parenthesis sub 0 shows so perfect agreement that no effect of distortion in changing measurably the value of E can be admitted. See tables 4 to 14. Turning next to assumption 1, this can be tested in 3 ways, all of which have been tried with negative results. First, a drop containing from 1 up to 6 or 7 elementary charges can be completely discharged, and its time of fall under gravity when uncharged compared with its time when charged. Second, the multiple relationships shown in the successive charges carried by a given drop may be very carefully examined. They cannot hold exactly if when the drop is heavily charged it suffers a larger drag from the medium than when it is lightly charged. Third, when drops having widely different charges and different masses are brought to the same value of L over A by varying the pressure, the value of E sub 1, which is proportional to open parenthesis V sub 1 plus V sub 2 close parenthesis sub 0, should come out smaller for the heavily than for the lightly charged drops. The following observations show that this is not the case. The last criterion is also a test for 2B, for if internal convection modifies the speed of fall of a drop, as Perrin wishes to assume that it may, it must play a smaller and smaller role as the drop diminishes in size. Hence, varying L over A by diminishing A cannot be equivalent to varying L over A by increasing L. In other words, the value of E sub 1 obtained from work on a large drop at a low pressure should be different from that obtained from work on a small drop at so high a pressure that L over A has the same value as for the large drop. Finally, if the density of a small drop is greater than that of a large one, see assumption 3, then for a given value of L over A, the small drop will show a larger value of E sub 1 than the large one, inasmuch as the computation of E sub 1 is based on a constant value of sigma. The fact then that for a given value of L over A, the value of E sub 1 actually comes out independent of the radius or charge of the drops, shows conclusively either that no one of these possible sources of error exists, or else that they neutralize one another so that for the purposes of this experiment they do not exist. That they do not exist at all is shown by the independent theoretical and experimental tests mentioned above. This removes, I think, every criticism which has been suggested of the oil drop method of determining E and capital N. Section 7. Summary of improvements in method. In order to obtain the consistency shown in the following observations, it was found necessary to take much more elaborate precautions to suppress convection currents in the air of the observing chamber than had at first been thought needful. To recapitulate, then, the improvements which have been introduced into the oil drop method consist in 1. A redetermination of eta, 2. An improved optical system, 3. An arrangement for observing speeds at all pressures, 4. The more perfect elimination of convection, 5. The experimental proof of the correctness of all the assumptions underlying the method, viz. A. That a charge does not alter the drag of the medium on the charged body, B. That the oil drops act essentially like solid spheres, C. That the density of the oil drops is the same as the density of the oil in bulk. Section 8. The experimental arrangements. The experimental arrangements are shown in Figure 1. The brass vessel D was built for work at all pressures up to 15 atmospheres, but since the present observations have to do only with pressures from 76 centimeters down, these were measured with a very carefully made mercury manometer M, which at atmospheric pressure gave precisely the same reading as a standard barometer. Complete stagnancy of the air between the condenser plates M and N was attained first by absorbing all of the heat rays from the arc A by means of a water cell W, 80 centimeters long, and a cupric chloride cell D, and second by immersing the whole vessel D in a constant temperature bath G of gas engine oil, 40 liters, which permitted in general fluctuations of not more than 0.02 degrees centigrade during an observation. This constant temperature bath was found essential if such consistency of measurement as is shown below was to be obtained. A long search for causes of slight irregularity revealed nothing so important as this, and after the bath was installed, all of the irregularities vanished. The atomizer A was blown by means of a puff of carefully dried and dust-free air introduced through the cock E. The air about the drop P was ionized when desired by means of Röntgen rays from X, which readily passed through the glass window G. To the three windows G, two only are shown. In the brass vessel D correspond of course three windows in the ebonite strip C, which encircles the condenser plates M and N. Through the third of these windows, set at an angle of about 18 degrees from the line XPA, and in the same horizontal plane, the oil drop is observed. End of sections 5 through 8.